All right. All right, we're going to continue with Gauss law. Yes, I'm going to put them on. All right, we started Gauss law by introducing the flux through a surface, which when the surface is flat and the electric field is uniform, we have flux of electric field equal to electric field times the area times cosine of the angle between them, which is basically E dot A, when we define A vector to be perpendicular to the plane and has the magnitude equal to the area of the plane. And then we said that if we have a non-uniform electric field but continuous and a non-flat or curved surface, especially closed surface, we define the flux out of the surface as integral E dot dA, where dA at any point is the little area vector on each one of these pieces, and it is directed outward from the closed surface. And some of them have negative contribution when the electric field is going into the surface, and some of them have zero contribution, some have positive contribution, and these are of course scalars. The total becomes a scalar. And then Gauss law says that this flux of electric field going out of any closed surface is equal to the charge inside, the net charge inside the surface divided by epsilon naught. This is Gauss law. And we said that it is equivalent to Coulomb's law, but it has more significance because it is also consistent with modern physics. And we obtained, from Gauss law, we obtained the Coulomb's law here for the electric field of a line of charge, infinite line, and electric field of an infinite plane. When there is symmetry, we can use Gauss law to find the electric field. And then we also said that there are some results that are not easy to get from Coulomb's law, but it is easy to get from Gauss law, like these: shell theorem for spheres, shell theorem for long cylinders, and also the electric field of solid sphere and solid cylinder. And in that case of a solid sphere, we said that outside the solid sphere acts like a point charge. If you have a solid sphere of uniform charge, when you're outside of it, you can put all the charge at the center and calculate the electric field like this: 1 over 4 pi epsilon naught, which is K Q over R squared, where R is the distance to the center. But when you are inside, we found that the electric field starts from 0 at the center and goes linearly to the surface. And then after that, it is like a point charge. So this is the characteristic curve for the electric field at any point at distance r from the center. If you are inside, means that little r is less than capital R, which is the radius of the sphere. You have a linear curve. And then if you're outside, it is 1 over R squared, as you see, inverse square law, like a point charge. All right, so that was the results that we found. Again, the same for the cylinder. Outside this cylinder, solid cylinder, the cylinder acts like an infinite line of charge. And inside is, again, whatever the electric field is at the center times the ratio of the R to R, means that it is linear with this little r. And we said that the charge per unit length, which is lambda, is proportional to the charge per unit volume with this relationship. We talked about that. And also we said that Gauss law requires that if you have any excess charge on a conductor, all the excess charge goes on the surface. There's nothing inside the conductor. And even if you have a cavity, but no charge inside the cavity, all the excess charge goes only on the outer surface of the conductor. But if you have a charge suspended inside the cavity of a conductor, then the opposite of that comes to the surface because of Gauss law. And then the balance of the total charge goes to the surface. For example, if you have Q, negative Q comes here. If the total charge of conductor is QC, then QC plus Q comes on the outer surface because there's negative Q in here. So the total charge of the conductor becomes QC plus Q minus Q, right? So this is the way the conductors work. And then on the surface of a conductor, just outside the conductor, the electric field is perpendicular, we said, and the magnitude of the electric field is proportional to the charge density, sigma. And in fact, electric field is charge density divided by epsilon naught at any point. So when there is a sharp, that's another story. When you have the surface with charge density, the electric field is proportional to the charge density. This becomes very important later on in the next chapters. We're going to talk about that. So, any questions so far? All right. And then we said that this also applies when you have two large plates at a very small distance to each other and have opposite charges. One has positive charge Q, one has a negative charge Q. This is, of course, idealized, and it is a correct approximation when the dimensions of these plates are much bigger than the distance between them, which is the case in case of capacitors that we're going to study later on. Then you see that it has a charge density sigma here, and the electric field outside is sigma over epsilon naught. In this case, it is uniform because they are large planes. And now we have this example. It says figure shows in cross section 3 solid cylinders, each of length L, and uniform charge density Q, concentric with each cylinder is a cylindrical Gaussian surface with all 3 surfaces having the same radius. Rank the Gaussian surfaces according to the electric field at any point on the surface. Greatest first. So first of all, it should say long cylinders, because we need to use the approximation when for infinitely long cylinder. All right, so what do you think the answer is? Any ideas? So we have the same charge Q on each cylinder. The cylinder is long, means that the length that is perpendicular to the page is much bigger than the dimensions or radius in here. What do you think? Of course, you need to use Gauss law, integral of E dot dA is equal to Q inside or enclosed divided by epsilon naught. If you use that, you see that the Q enclosed is the same, right? And there are 3 cylinders with the same area, so the electric field should be the same on the surface. So basically, because of symmetry, E dot dA becomes E times dA, and then this becomes E times 2 pi r, if r is the radius of the Gaussian surface, 2 pi rl equals to Q over epsilon naught, and you see that the electric field is the same for all of them. All right, so the ranking is E of A is the same as E of B is the same as E of C, right? Does it make sense? Do I have your voice? Do you hear me?
Yes.
Oh, okay. I thought maybe I lost you. All right, so all of them equal. What about this one? Figure shows in cross-section a central metal ball. This is the central metal ball. And two spherical metal shells. This is this one and this one. So two metal shells. So you see the cross sections. And three spherical Gaussian surfaces of radii r, 2r and 3r. You see the Gaussian surfaces are drawn like circles because the cross section of a sphere is a circle, and they have radii r, 2r and 3r with the same center. The uniform charges on the three objects are ball Q, smaller shell 3Q, larger shell 5Q. Rank the Gaussian surfaces according to the magnitude of the electric field at any point on the surface. Greatest first. What do you think? Again, we use Gauss law. The integral E dot dA over closed surface for any surface is Q inside divided by epsilon naught. What do you think? So here we have Q here. 3Q is on the smaller shell and 5Q is on the larger shell. Any ideas?
Wouldn't the smallest shell get the largest? So it would be like one.
Let's call them ball. No, sorry. You have Gaussian surfaces. We want to rank the Gaussian surfaces, right? So call this S1, S2, S3. Or now you can call the electric field on the surfaces E1, E2, and E3. So how do you rank the three? One, two, three. Somebody says 1, 2, 3. What about others? Do you agree, disagree? And everybody agrees with that. 1 is bigger than 2, bigger than 3. Why is that?
Because I was like looking at our equation that we set up previously.
Uh-huh.
The same, like we'll be using E equals 2 pi r L equals to Q over E naught.
All right, 2 pi RL was the surface area of cylinders. Now here we have surface area of a sphere because our Gaussian surfaces are a spherical Gaussian surface, right? So in the previous problem, these were cylinders. The cylindrical Gaussian surfaces. Now here we have a spherical Gaussian surfaces.
Would we use the formula KQ over R squared and then the ratio between the radius?
KQ over R squared. Yeah, it becomes similar to the Coulomb's law, but What does this Gauss law say? If you do the same thing that I did with the spheres, you see E and dA are in the same direction, so it becomes integral over the surface of E times dA equal to, for each one of the surfaces, Q inside over epsilon naught. And then E is the same because of symmetry comes out, and that becomes E times the total area, which is 4 pi r squared equal for r because Q inside over epsilon naught. So for each one of the Gaussian surfaces, you can write this. But for S1, what is the radius? Radius is r, right? So E times 4 pi r squared is equal to Q inside, which is, well, how much charge is inside S1? Can you tell?
1 Q.
One Q, right? That's Q over epsilon naught. So therefore, E is E1, let's call it E1. E1 is Q over 4 pi epsilon naught r squared, right?
Professor,
Yes,
why are we using 4 pi r squared? Aren't the what is it called? Aren't we looking at spheres?
yes, sphere.
So would we be using the formula of the volume or the, oh, this is the area, the surface
Yeah,
area. Okay.
yeah, this is the total area, isn't it?
Okay, yeah, my
The
bad.
total area of 4 pi r squared. No, it's
Thank you.
okay. All right, so this is for S1, E1 is this, right? What do I get if I write for S2? You have E2 times 4 pi, and the radius is what for the second one?
2r.
2r squared, right? Equal to how much charge is inside that? How much charge is
3q.
inside S2? There's a Q on the ball, and there's 3Q on the inner shell, the first shell, the smaller shell. So the total charge that is inside S2, look at S2, focus on that. The total charge that is on inside that, there's a Q here and 3Q in here. So the total charge in there is 4Q, right? Over epsilon naught. And this 2 squared and this 4 cancel out. And then E2 becomes Q over 4 pi epsilon naught r squared again, right? And what do I get if I write that for S3? Becomes E3 times 4 pi. What is the radius?
3r.
3r squared, right? Equal to
6q.
5q on that, 5q on the outer share, and 4 on these,
9, sorry.
9. 9q over epsilon naught. Again, this 3 squared and 9 cancel out. You get E3 the same. Right?
So they're all equal.
They are all equal.
So
So E1 is equal to E2 is equal to E3. Right? Because as you increase the radius, you increase the charge inside as well. And exactly the same way. You have 1q in the first one, 3q in the second, and 4q in the second one, and 9q in the third one. Right? Makes sense?
so yeah, so if there's a Gaussian surface and then there's like another Gaussian surface that's like, or Gaussian surface that's like more out or like has a bigger radius, we still add up all of the previous charges.
Yeah,
inside.
what if there was another surface here
Mhm.
with the radius of 5r? What would be the electric field at the surface of this one?
Epsilon or
Yeah,
E4 and then
let's call it E4, right?
E4 times 4 pi.
For S4, so E4 times 4 pi times 5r squared equal to what is the charge inside?
mm,
It'll be the same ones, 9Q.
That's right, the same, 9q divided by epsilon naught. And now you see that the 9 doesn't cancel. It becomes E3 becomes 9/25 of q over 4 pi epsilon naught r squared. Now for that one, 9/25 is less than 1, so it's less than, sorry, this is E4. So E4 is less than E3 and less than the other ones. You see, but it happens in this case that the charge increase goes with the radius squared. They get the same electric field at the surface, right? Does it make sense? So you see, this is we apply this all the time. Any questions?
Professor, it should be 9/100.
No, 5 squared. I have 4 here as well.
Oh, okay.
I just want to compare with the other ones. So this part is the same. All right. Okay, so now I'm asking, what is the charge on the inner surface of the smaller shell? And what is the charge on the outer surface of the small shell? This is the small shell, you see, this one. What is the charge on the inner surface of the smaller shell? What do you think? The shell has a thickness. There's an inner surface and outer surface.
Is that like the charge where there's only a charge on the outer surface and then no charge on the inner surface? Or
That was like a cavity. That can be considered like a conductor with a cavity, right? But inside the cavity, there is charge here, right?
yes,
This is conductor with a cavity. It has an outer surface here, an inner surface here, right? So what we said about the cavities applies here, right? So what do you think if there's a charge Q inside here? What is on the inner surface? Yeah, on the inner surface will be negative Q, right? So if I draw that, you see this is, sorry. If I draw the shell a little bit bigger, this is the outer surface, this is the inner surface, and this is charge Q here. So negative Q comes to the inner surface, and the balance total Q total is 3q, right? So the balance should come out at the outer surface. So the total is 3q, but we have negative q here. So q in equals to negative q. Q out is what? It's a q inside plus q outside equal to q total. So q inside is negative q plus q outside equal to q total, which is 3q. So it's a q total should be equal to 4q.
I mean Q out, right?
Oh, so q out, right? Thank you. Q out will be 4q. Right? So Q in will be on the inner surface of a smaller shell will be negative Q. We call it Q in, and Q out will be 4Q. Although the total charge is 3Q. So it has 4Q outs on the outer surface and negative Q on the inner surface. So the total is 3Q. Make sense?
Professor, could you explain how we got negative Q as being Q in real quick again, please?
Yeah, negative Q is inside, because if you take, we said that if you take a Gaussian surface that is completely inside the conductor like that, the electric field is 0 here. Inside a conductor, electric field is 0. Because if it is not 0, conductor has plenty of electrons, they move. Okay? The electrons move and they adjust themselves until the electric field is perfectly 0. So if you take a Gaussian surface there, then for this Gaussian surface, if you write integral of E dot dA equal to Q inside enclosed divided by epsilon naught, E is 0 everywhere on the surface. So this integral is 0. That means that Q enclosed in 0. Q enclosed is 0. Therefore, if there is a Q here, there should be negative Q somewhere, right? And then if you make this Gaussian surface smaller and smaller, approach it to the inner surface, but keep it inside conductor, you see that that negative Q has to be on the surface of the cavity or the inner surface of the shell. All right, this is what we said. Remember what we said here. Why did we say there's a negative Q here? For E to be 0 at all points on the Gaussian surface, this Gaussian surface that's purple, the surface of cavity must have total charge negative Q, right? And then we have this now, this shell as a conductor with a cavity, right? Because there's thickness here. All right. And on that surface, on the inner surface, therefore, it is negative of what is in the inside the cavity. Right? And on the outer surface is the balance. Whatever is left goes on the outer surface. So negative Q is on the inner surface, 4Q is on the outer surface. Does it make sense?
Yeah, that makes sense. All right, thank you.
You're welcome. All right, now let's do the same thing for the larger shell. What is the charge on the inner surface of the larger shell? Now looking at this one. What is the charge on the inner surface of the larger shell? And what is the charge on the outer surface of the larger shell?
4Q.
The inner, somebody says, Tanas says negative 4Q. Everybody agrees? That is correct because 4Q is on the inside the cavity of that one, 4Q. So negative 4Q comes to the inner surface of the large one, and the balance goes on the outer surface. So here is negative 4Q. That's correct. So what is Q outer? What do you think?
Positive
Well,
9Q.
9Q, the balance again, because there's total of 5. If there's negative 4 on the inner surface, the outer surface gets 9Q. All right. Any questions?
Yeah, I can you kind of like draw out where the I guess the charges or the field is, because I'm looking at this diagram and I'm looking at the Gaussian surface. So
Gaussian.
inside the Gaussian surface, there's a positive, I guess charge or electric field, right?
Yeah. No, the charge, electric field.
Yeah.
Electric field is created by the charges.
Okay, so
But- Yeah.
there's positive inside the purple, which is positive, but then outside of the purple, which is inside of the shell still. there's
No,
a
we're just looking at this that has thickness, you see?
Yeah.
This is the conductor. It has inner surface here and outer surface here.
Okay.
Okay? This is the outer surface and inner surface. It's hard to draw,
Okay.
right? So if you exaggerate that thickness, you have an inner surface and outer surface. So
Okay.
because there are positive 4Q here inside,
Mhm.
the Gauss law requires that negative 4Q should be on the surface. And then because the total charge of the shell is 5Q, then plus 9Q should be here so that the total is 5Q.
And you're referring to which shell in this case? Oh yeah, the outside one.
The outer shell. But the shell has a small thickness. I'm just exaggerating it to make it more clear,
Mhm.
right?
Okay.
So negative 4Q comes on the inner surface and positive 9Q goes on the outer surface, and the total charge of the shell is positive 5, is 9 minus 4. Okay. I hope that's clear. So let's move on. Here we have an electron is released between two infinite non-conducting sheets that are horizontal and have uniform surface charge density sigma plus and sigma minus, as indicated. The electron is subjected to the following 3 situations involving surface charge densities and sheet separation. Rank the magnitudes of the electron's acceleration greatest first. So there are 3 situations, 1, 2, 3, as you see here. In situation 1, the sigma is sigma plus, means the sigma of this one is a positive 4 sigma, a certain value of sigma, and negative 4 sigma for sigma minus. So these two for situation 1. And the separation of the two infinite sheets, infinite non-conducting sheets, the separation is D. And in situation 2, we have 7 sigma and negative sigma, and the separation is 4D. And in situation 3, we have plus 3 sigma and negative 5 sigma, and we have the separation 9D. Rank the magnitudes of the electron's acceleration greatest first for the 3 situations. What do you think?
Don't we have to set up F equals QE here?
Yes, F,
Mm.
F, not QE, F is equal to MA, acceleration,
Oh,
mass of electron acceleration. So, and the force is equal to E times E. So the force equals MA, and a force is equal to the electric field times electric charge equal to mass times acceleration. Therefore, the acceleration is basically proportional to electric field. So E over M times the electric field. E and M are constant, are the same for the electron, but so means that the larger the electric field, the larger the acceleration. So which one, the question is, which one creates more electric field? Situation 1, 2, or 3?
one.
Why is that?
Because the radius is the smallest, and when we combine,
Hmm.
oh, are those charges or?
These are infinite non-conducting sheets
All right, never mind.
that are horizontal and have uniform surface charge densities sigma plus and sigma minus. This is sigma plus, sigma minus. Any ideas? All right, what did we have about infinite sheets? What is the electric field of an infinite sheet of charge?
Sigma over 2 E.
That's right.
No?
That's right. E was sigma over 2 epsilon naught. So you need to focus on this formula. What does that tell you? And of course, this is just the magnitude, and the electric field direction is perpendicular to the plane and is away from the positive plate and toward the negative plate. Right. So for example, situation 1, we have two electric field, one due to this upper one, let's call this E1, and another one due to the other one, E2. Right? And E total is equal to E1 plus E2. Right? Because they are both in the same direction. For E1 is away from the sheet, the upper sheet, which is downward. For the lower sheet is toward the lower sheet, which is still downward. So they add up, right?
So they are equal to each other.
They are equal because you see this becomes E1 plus E2. E1 is sigma 1 over 2 epsilon naught, and the other one is sigma 2 over 2 epsilon naught. Therefore becomes sigma 1 plus sigma 2 over 2 epsilon naught. So it is actually absolute value of these we should consider, right? So E for situation 1 is equal to 8 sigma over 2 epsilon. What about that in situation 2?
Same thing.
Yeah, you see 7 and 1 again. The last one is 3 and 5. So E2, E situation 2. And is the distance a factor?
No.
No, because the electric field of an infinite sheet doesn't depend on the distance. Right? It
What is-
creates
Oh, sorry.
it creates a uniform electric field everywhere.
What does epsilon not stand for again? Just like,
The constant.
Okay, okay,
Epsilon naught is 1 over 4 pi k, remember?
okay, okay.
Which is 8.85 times 10 to the negative 12. And the unit is Coulomb squared over Newton meter square. All right. And then electric field in situation 2 is also absolute value of sigma 1 plus absolute value of sigma 2. Actually, this should be absolute value of each one together. Divide by 2 epsilon naught. Again becomes 8 sigma over 2 epsilon naught. And in the third one also, ES3 is also 8 sigma over 2 epsilon naught. So all of them have the same electric field and therefore the same acceleration for the electron. So the ranking is same. You see, it's just a matter of figuring out what is the formula for the electric field. The formula is this. Sigma over 2 epsilon. Of course, here we have 2 of them, then you add them. So for example, for first situation, both electric fields are the same and in the same direction. For the second one, the first one is much bigger. The second one is smaller, but then sum of them is the same. For the third one, the first one is smaller, the other one is bigger. So this is 7 and 1. This is 3 and 5. This is 4 and 4. Right? It makes sense?
Yep.
All right. Here, sorry, my
Wait,
chair is squeaking. I hope it doesn't make a lot of noise. Yes?
Can you go back?
Yeah.
What's making you decide that to become positive for, like, what made you draw the arrows in those locations? I mean, but
Yes, you see that E1 is for the upper plate, which is has a magnitude of sigma over 2 epsilon naught. It should have an absolute value here. It doesn't matter because that's a magnitude. Is sigma over 2 epsilon naught, and it is perpendicular to the surface and away from the surface if the charge is positive.
okay.
So at this point, any point in here, it is away from these positive charges. And for this lower one, it's toward the positive negative charges.
Which is E2.
Yes.
And E2 is equal to 8 sigma over 2.
No, E1, E2 is 4 over 2 epsilon naught, and E1 is 4 over sigma over 2 epsilon naught. The sum of them is 8.
Which ones again? I didn't see those.
This one is 4 sigma over 2 epsilon naught.
Okay.
And this one is also 4 sigma over 2 epsilon naught. They add up. This plus that becomes 8 sigma over 2 epsilon naught. Right?
Yeah.
And in this case also they add up to 8. In this case also they add up to 8.
Okay. Now if one of them is, and that's all referring to the point that you said, because that's the main charge, right?
Any point are inside between the two plates.
Okay, I see what's going on. So okay, all right, I'm starting to see that more. And that's a charge that's basically like an electron, right?
That's right. Yeah,
because we're considering the
electron is inside. Yeah,
like we can assume this is copper. Can I say that?
It doesn't matter what. No, it is not. It says non-conducting sheets. So
it's a non-conducting.
Yeah. See, infinite non-conducting sheets. Right.
Professor, why is one positive? Why are both of them positive? Isn't one negative? Because the electron's a negative charge, right? And wouldn't that attract towards the positive plate?
It doesn't matter. You see, the acceleration of electron will be up, but that's proportional to the net electric field, which is down. Both of the vectors are down, so they add up. And each one has a magnitude of 4 sigma over 2 epsilon naught. Right, so this formula just gives you the magnitude, and the direction is according to which is perpendicular to the plane, and it's away from positive charge, and it's toward the negative charge. For the upper plate, below the upper plate, the electric field is downward. Above the lower plate, for the lower plate, the electric field is downward also. So both of them happen to be in the same direction. If you wanted in this situation, at this point, then it would be different. You see, at this point, the E1 will be away from it, from the upper. This is E1, means for the upper, let me call it E up. And for the lower one is toward it, so it will be this way. E
Towards a
down.
positive sheet.
No, away from positive toward negative. For
So
this
then-
one is negative. So the electric field at this point is down. This one is positive. The electric field of that is up, away from it. So each one of these, each one of these plates create an electric field at this point.
And what about the sheet though? I mean, how would would that E down, that charge
me-
go right through the
Let me
sheet?
call it E plus, E minus. That's better.
What about the sheet though?
Yeah, the sheet.
Would it just go right through that positive sheet?
What do you mean? What goes through this?
Yeah,
This
'cause
this sheet creates an electric field. You keep forgetting that the source is the sheet.
Mhm.
The source of electric field is the sheet. So at any point around it, it creates an electric field. So at this point, it is away from the positive. The positive one creates an electric field this way,
Yeah.
E positive.
Mhm.
The negative one creates an electric field that is toward it. So it creates an electric field this way.
Mm.
They
Okay.
cancel each other here. But in between is the same. The positive one creates an electric field that's away from it, E positive. The negative one creates an electric field that is toward it, the same direction, E negative. Right?
Okay, then.
Yeah, so at any point they create an electric field. But this is the formula. The formula says the electric field doesn't depend on distance. It only depends on how much charge density is on the sheet. And is away from the sheet if the sheet is positive, toward the sheet if the sheet is negative. So if the electron was outside, not in between the two sheets, but outside the two sheets, then these wouldn't be the same, because these two in situation one cancel each other. In situation two, so this is situation one. In situation two, let me write it here. In situation two, you have 7 sigma for positive. That means you have a vector 7 times bigger in this case, E positive, and 7 times smaller, E negative. And then there you see that there's a difference. They don't cancel each other because E plus is 7 times bigger than E minus. But this is situation 2. In situation 3, let me write here, situation 3, E plus is 3, and E minus is 5. So E plus is here. Of course, these are continuing here. E plus is 3, E minus is 5. So there's a balance that's downward. This is situation 3.
Why do you use E though? Can't you just use the sigma signs?
Sigma is just the charge. E is the electric field.
Oh, okay.
Sigma is a scalar. I cannot draw vectors for sigma.
Okay, so it's almost the same thing. However, charge,
That's right. Because
charge and field is two different rules.
yeah, there are two different things, but the electric field
Okay.
is a vector and its magnitude is proportional to sigma.
Okay, I see what's going on.
Yeah. So you need to think about this stuff, you know, no matter how many times I say it, if you don't think about it, you don't get it. You should go home.
I guess I was just confused on both those, I guess, bars, the positive bar and the negative bar.
These are not bars, these are a cross section of infinite sheets.
Yeah, the sheets.
Right? You need to imagine. You need to imagine what's going on.
Mhm.
All right?
Okay.
Yeah, every time I teach you something, anyone teaches you something, you should go back and think about it, imagine what's going on. Otherwise, it just comes in from this ear, goes out of the other ear.
Yeah. No, I'm sorry. I see it though. I mean, I understand those rules of,
Mhm.
the electric fields and the charges.
Yeah.
I think this is something we've done before already, but we're just applying the formula now.
That's right. We have done that, and now we're using the formulas. All right. So, how much time do we have? All right, so almost an hour. So let's do this one. Now, imagine what is going on. 4 situations in which 4 very long rods, see, these are rods, extend into and out of the page. We see only their cross sections that are these little circles. So they're going out of the page. The value below each cross section gives that particular rod's uniform charge density in microcoulombs per meter. So that gives you lambda, right? We call it lambda. The rods are separated by either D or 2D as shown. And the central point is shown midway between the inner rods. Rank the situations according to the magnitude of the net electric field at that central point, greatest first. And do you understand the situation? Now it's like instead of this, now it is, imagine it is like that, 4 long rods like that. And we are just looking at their cross section here. And there's a midpoint here. We want to see what is the electric field at this point. So the electric field is the vector sum of the individual electric fields of the rods, long rods. And what is the electric field of a long rod? Infinite rod. Who remembers that? The electric field of infinitely long rod of charge density lambda.
Was it pi r squared p or something?
Pi r squared pi? Pi r squared what? It was in terms of lambda. So it was 2k lambda over r with infinitely long line of charge, remember?
Yes.
I had a more general formula, and they say if you have an infinitely long rod or wire of charge density lambda, it reduces to this. All right. And then, of course, this is the magnitude and the direction is directly away from the rod or directly toward the rod, depending on whether the charge is positive or negative, right? So in part A, in situation A, we have positive on the left side, negative on the right side. So let's call these ones 1, 2, and 3, and 4. Which direction is the electric field of each one, and how much is it?
From positive to negative.
From positive means from left to right, right? Yeah, for number 1, it is this way, right? This is E1, right? Because it's away from it, because it's positive. For number 2 is also that way, E2. For number 3, it is toward it, so it is the same way. For 4, it is also the same way. All the same way. So they all add up, right? But how much is each one? So we have, let me call it A. EA is equal to 2K lambda. The lambda is 3. That's a 3. 2K times 3 divided by R, which is the distance from here. So this is R to 1. This is R1.
So it's 2D.
Yes, R is 2D. 2D. So it becomes 3K over D, basically. Right? Plus, before I do that, plus for this one, for the second one, it becomes what? Becomes 2K times 2 divided by 1D, right? Plus for the other one becomes another 2K times 2 over D, and the other one becomes 2K. This is, I'm writing electric field equal to 2K lambda over R. R is the distance. 2K times 3 again, divided by 2D. So this becomes 3K over D, this becomes 4K over D, 4K over D, and 3K over D. So the total becomes 3 and 3, and 4 and 4, 6 and 8, 14. K over D. Right, so this is in part A. Now for each one you can calculate and then compare. What do you think the result is in B?
There's 2 going to the left and 2 going to the right.
Mm-hmm. Yeah, no net electric field. That's correct. Yes, you see, for the first one, oops, sorry. For the first one, you get an electric field this way, E1. For second one, you get an electric field this way, E2. That's larger because it's toward it. For the third one, you get an electric field that's the same as E2, but opposite that. So these two cancel each other, E3. And for the fourth one, it is also away from it. So it is, and it is the same as E1, so E4. To one side, to the other side, each one is the same as the other, so they cancel. E, B is equal to 0. What about C? Again, call this 1, 2, 3, 4.
I think the net electric field is going towards the left.
Toward left, that's correct. So let's do one by one. 1 creates this E1 because it is positive, and away from it. 2 creates an electric field that is toward it. So that's this way, E2, maybe larger because closer. And 3 creates an electric field that's away from it and is the same as E2. So we have this, E3. And for the fourth one is away from it, is the same as E1. So it comes like that, E4, and then E1 and E4 cancel each other, and E2 and E3, they add to each other. So the net becomes just due to E2 and E3, right? What about D?
They cancel out.
They completely cancel out, yes. So 1 creates an electric field this way. Oh God.
Just curious, what are the distances?
The distances are 2D. If you want to write them, let me write for E in part D, I should write 2K, lambda is -6, so it is the 6th magnitude, divide by the distance is D, this is D, this is 2D, so 3D. The distance to the field point,
Okay.
from here to the field point is 2D, and this is D, becomes 3D. And that is in this direction, so I put a negative sign. And for the 5, for E2, this is E1, E2 is this way. So it's positive. What is the value? 2K and lambda, which is 5, divide by D, right? And then for the 3 is positive, becomes this way, E3. So it's negative 2K 5 over D. For the last one, it is negative, so it is toward it. It's this way, E4. And the value is 2K times 6 divided by 3D. So you see, this one cancels this one, and this one cancels this one.
Okay.
So E in part D is also 0. And in part A, it is just the same as, sorry, part C is the same as this plus that, because the other two cancel each other. So the ranking is clear. Which one is biggest?
A,
Yeah, EA is the biggest
C,
and greater than EC, greater than
BB.
BB, and is equal to ED, and both are 0. All right. So you see, first you use the formula that was for the long rod, and then this is just the magnitude. You need to look at the direction. Direction is away from the line of charge if it is positively charged. It's toward the line of charge if it is negatively charged. Okay. Any questions? All right. Here, figure 23.27, which is what you see, shows 4 solid spheres, each with the charge Q uniformly distributed through its volume. Rank the spheres according to their volume, charge density, greatest first. The figure also shows point P for each sphere, all of the same distance from the center of the sphere. Rank the spheres according to the magnitude of the electric field they produce at point P, greatest first. So which one has more charge density? If they all have the same charge.
A.
A has more charge. The smaller it is, the bigger the charge density. So rho of A is greater than rho of B, is greater than rho of C, is greater than rho of D. And which one produces more electric field at point P? We call them E1, E2, EA, EB, EC, and ED.
EA and EB are the same.
EA produces the largest amount.
Yes,
Oh, no, wait.
EA and EB are the same.
Yeah,
yes, EA and EB are the same. Very good. Because
Because they're the same charge, and like if it's a circle, we could assume that all of the charges at one point. And
yes,
since
that's right.
they share the same radius as well.
That's right. Because no matter how much the radius is, as long as you're outside the sphere, you can put all the charge of the sphere at the center and consider it as a point charge. So EA is equal to EB. What about C and D?
They would be 0, right? Because if the point P is inside, then we would assume that there's no electrical field acting on it.
That is that we said for spherical shell. Are they spherical shells?
yeah, that's what I was thinking too, that I'm assuming they aren't spherical shells, but I mean,
So read that again. Shows 4 solid spheres. So
Yeah,
they are filled inside.
so it's technically not,
Not
is it uniform?
is not hollow. They are not hollow.
Yeah.
They
But
are
it's still uniform though, right? Because
uniform volume
elec-
charge density. Yes, it says
Yeah.
volume charge density, right?
yeah, because up to that point, the electrons are obviously towards the edge.
Mhm.
So that would mean that with that point, if you consider the electrons on the edge of the sphere and the point P, depending on if it's gonna have if you apply the same rules we applied before, one side of the P, which is the top side, is gonna have like a positive or a negative, and then on the lower end it'll have like a positive going towards the center.
Mm.
Does that make sense?
I don't know. We're talking about electrons. This is charge distributed over a sphere. So we want to find the electric field here. You can use Gauss law, integral E dot dA equal to, for a Gaussian surface, Q enclosed divided by epsilon naught. What if you see, if you use a Gaussian sphere here at the radius R for all of them, what do you get?
That they're all equal.
No, the first two have the same enclosed charge, which is Q, right? For the first two. That's why when you do the math, you get E times 4 pi R squared equal to Q over epsilon naught for A and B. But for C, Q enclosed is less than Q, right? Because some of the charge is not inside that Gaussian surface. Some of it is outside. In part A and B, all the charge Q is inside the Gaussian surface. But in C and D, some of the charge is outside. Does it make sense?
No. Can you kind of elaborate? Like,
Do you see the Gaussian surfaces that I drew?
yeah, the surfaces,
Yeah, how much charge is here inside this Gaussian surface?
I mean, wouldn't it?
This is each
It'd
with
be
charge
positive.
Q. All of them have charge Q. All of the
Okay.
Q is inside here, right? All of Q is inside. Here, all of Q is inside. But here, some part of Q is inside in part C.
Oh,
And in D, only part of Q is inside. But which one has more charge, in C or D?
see,
C has more charge. So the more charge is inside, the more electric field you get because of this, right? Or this is Q enclosed, right? So the more charge you have inside, the more electric field. So here, the charge enclosed, Q enclosed for C, Q enclosed for part C is less than Q. But Q enclosed in part C is greater than Q enclosed in part D, right? So you see that EA is equal to EB and it's greater than EC, and EC is greater than ED. All right. Because E times 4 pi r squared, this is all the same. 4 pi r squared is the same, epsilon naught is the same. So the more charge you have inside, the more electric field you have, right? On the surface of the Gaussian surface. All right. All right, we have only 2 minutes and this problem is long. I have a video about the problems like that. You can find that by this link. It is on my YouTube channel. All problems number 2, 9, 11, 10, 13, 16 are similar to this. And let's do this one for the time. Yeah, I will post the slides. Here we have a charged particle is suspended at the center of 2 concentric spherical shells that are very thin and made of non-conducting material. Figure A shows a cross-section of this system. Figure B gives the net flux phi through a Gaussian sphere centered on the particle as a function of the radius r of the sphere. So it means that you're doing sphere like that, a sphere like that. These are Gaussian spheres, and as the radius increases, we measure the flux through it, and this is what we get. It's constant up to here, and then suddenly jumps and it becomes constant here, and suddenly jumps up, becomes constant here. That is flux as a function of the radius of the Gaussian surface. The scale of vertical axis is given. What is the charge of the central particle? What are the net charges of shell A and shell B? All right, I think we are out of time. So I will put these on, there's a few more examples. There's so many of them. So see, when you guys need to go think about it so that when I talk to you about them, when I refers to something, you understand what I'm saying. Otherwise, we're not going to get anywhere at this speed. All right, so you need to imagine, you need to go home and sit down and think about these things. What is going on? It's not just a story, a roman, a novel that you just read and enjoy. You need to think about what it means and understand it in order to be able to apply it later on. All right? So yeah, do that. And I don't know, I need to move on probably. I need to look at the calendar, see how far we're just in the third chapter, and we have 10 chapters to cover. So actually 12, maybe 11 chapters to cover. So I need to move on. All right. Maybe I move on to the next chapter next time. And then if you have time, come back and revisit some of these. Any questions?